Alright, hello everyone, welcome to another video. This is the second video on 2A2, which is about gas laws. We're going to talk about Maxwell-Boltzmann curves, or Maxwell-Boltzmann thermal distributions, as it's sometimes called, although I like Maxwell-Boltzmann curves because thermal distribution just sounds a little too hoity-toity for my liking. Alright, well let's think about something here. Or let me state a fact. How about that? We'll state a fact and then we'll think about something. Alright, I'm going to tell you that temperature equals the average kinetic energy of a substance. Okay? So if I have something that's really, really hot, that's because the average kinetic energy is really, really hot. So if you think about it, temperature is really just a measure of speed. Not, well, kind of speed. Kinetic energy, which, as you know, is not necessarily speed. Because it takes into account mass. But anyway, so temperature is essentially speed for our purposes. Well, we can graph that. So let's say we have something at absolute zero. I'll put temp down here, and I will put number of particles on this side. All right, so I have temperature and number of particles. Well, if something is at absolute zero, at 0 degrees Kelvin, that means the average kinetic energy has to be 0. Well, that means that every single particle in the sample must be moving at 0, or must have a kinetic energy of 0. So that means my Maxwell-Boltzmann curve will actually have a straight line right here at 0. Right? Because all of my particles would be at 0 degrees Kelvin. That makes sense. In order for me to have a 0 average, that means there cannot be anything above 0, otherwise that would skew my average up. So, my average is 0. Now let's talk about what happens when I start heating it up, because nothing's really at absolute 0. Alright, so here I have temperature, and here I have number of particles. So Maxwell and Boltzmann actually started heating things up and measuring the average kinetic energy of those compounds. Now let's say this is 0, and instead of at 0, it's at now 10 degrees, or 10 Kelvin. All right, so it's at 10 Kelvin. Well, this is an average, right? This is an average. This is the average kinetic energy. So some particles will be above 10, some will be below 10, but most of them will be at 10, because that's what the average is. So I will have something that actually looks a little bit like a bell curve. So my bell curve is very, there we go. That's bell curvy-ish. Anyway, you get the idea. So the maximum, actually let me make that a little bit smaller. There we go. That didn't really help very much. There we go. If you hear people excited, it's because gaming club's going on next door, and they're more exciting than me. So here I have a bell curve. All right, most of my particles are at 10 degrees Kelvin, or 10 Kelvin. But I do have some with less, and I do have some with more. This is the average. Notice a couple of things. As the temperature went up, the height of my peak went down. That's because if this is percentage-wise, I don't have 100% of my samples at 10. I have less than, because there's some on either side. Well, let's say we have another Maxwell-Boltzmann curve. Let's do it down here. I still have temp here. I have my hashtag part, which is really number of particles, whatever. Let's say I heat up to 300 Kelvin. That's way too far over. That's not going to work. Let's say I heat it up to 300 Kelvin. 300 Kelvin is right around room temperature. So if it's at 300 Kelvin, my Maxwell-Boltzmann curve will look like this. All right, because now my average is starting to spread out a little bit. Now that it's at 300 Kelvin, I have more particles that can be at can be farther away from it. Because if we extrapolate it from 0, it had to have been a vertical line, because the average of 0 has to be 0, right? I can't have anything with some temperature, because then my average wouldn't be 0. My average would be something. But since my average has to be 0, I can't have anything other than 0. And as I move away from 0, my curve starts to flatten out. So this is a higher temperature. It doesn't look like it's a higher temperature because the peak of my curve is lower, right? And we think of higher temperatures as higher. But in reality, the peak has been shifted over. And as the farther I shift over my peak, the flatter it becomes. So I started initially at 0 Kelvin with a straight vertical line. At 10, I had this guy. And now at 300, I have this. Okay? So you can see that as my temperature increases, my curve actually starts to flatten out a little bit. And that's simply because I have a wider temperature range to get my average from. Right? It follows a bell curve distribution. That's a Maxwell-Boltzmann curve. It's not too tricky, but it's just important to realize that temperature is average kinetic energy. It's not the kinetic energy of every particle. Not every particle is going to be moving at have the exact same kinetic energy. And just as importantly, kinetic energy is not necessarily speed. Okay, kinetic energy is not necessarily speed, even though I talked about it being speed earlier in this video. For example, helium, which has a mass of 4, and argon, which has a mass of, well, I can't say 40. I should put that 40, yeah. All right. Argon, or helium, has to move 10 times faster, right? Because kinetic energy is mass times velocity. Since helium is lighter, in order to have it have the same temperature, the same kinetic energy, it has to be moving faster. This one has to move faster. This one has to move slower. So for these two to have the same temperature, the same kinetic energy, they can't be moving at the same speed. They have to have the same kinetic energy, which takes into account mass. So heavier particles are hotter at slower speeds than lighter particles, because it takes into account mass. All right, hopefully that cleared up temperature and Maxwell-Boltzmann thermal distributions. Have a great day.